Okay, folks, good morning, good morning, good morning. Let me share my screen and let's get started. Okay, let me get out of this here. Let me do this. Okay. All right, so let's get started with today's class. Before we begin, let me state, you probably saw the announcement. I think I posted an announcement concerning when assignment number 3 is due. And that assignment is due on Friday. All right. So if you have not submitted it yet, please do so. I've created a Dropbox for it, so you should be able to upload your assignment into that Dropbox, and it's due on Friday at midnight. Make sure, as I said before, that it's done in ink, blue or black ink. Make sure also that your name is written at the top of every page, all right? And also make sure that it is submitted as a PDF document, okay? So with that out of the way, let's start talking about acids and bases. And again, I'm assuming or presuming that you would have watched the video lectures concerning that particular chapter. So before I begin, are there any questions you guys have concerning anything you have seen in those videos? Any questions? Any questions?
Yeah, I have a question.
Yes, ma'am.
The second video link that you put up called pH and POH, it wouldn't open for me. It kept saying video unavailable. This video is a duplicate of another YouTube video. So I didn't know if anyone else had that problem.
Let me see. Let me see here. So you're saying the second video or the...
Yes, the second.
Okay. Let me try it here and see. Oh, interesting. Okay, I have to look into that. I didn't realize that that is the case. All right. So I apologize for that. I didn't know that there was a problem before now. And this underscores the importance of, contacting me whenever if you guys encounter any issue of this type, please let me know as soon as possible. Just shoot me a quick email and I'll try to take care of it. All right. But I don't know what the problem is. I have to look into that. So I'll try and look into that after, well, maybe by tomorrow, because I have a full day today with teaching. All right, so I apologize for that. But what I can do is actually cover some of that discussion in that video right now, all right? So that you should be able to do the questions we're about to get into. Okay, any other questions? Any other questions? Okay, so let me first, I think last time I started talking about acids and bases, and I started talking about the relationship between conjugate acids and conjugate bases. So let me just remind you, let me go to my writing thing here, what we mean by those terms. So an acid, if you remember, is a substance, and there are several definitions. The one that we're working with here is a Bronsted-Lowry definition. An acid is a substance which gives up a proton to a base, right? And the base is a substance which accepts the proton, all right? Remember, the hydrogen ion is the same thing as a proton, all right? So in this particular hypothetical example, this is your acid, and this is your base, all right? So when it comes to this side here, the species that results from losing a hydrogen ion from the acid, that is called the conjugate base of the acid. Conjugate base, all right? And the species that is formed when a base gains a proton from the acid, that is called the conjugate acid. All right. So basically understanding what we're discussing here will become important to answering the questions for number 1. Okay, so based on what we have just discussed here, this question says labeled acid A, base B, conjugate acid CA, and conjugate base CB in each of the following reactions. All right, so based on what we have just discussed here, what would you say H2SO4 is? Anybody?
An acid.
Exactly. Okay, very good. And the NH3 therefore would be the base, right? Okay, so usually this is where students tend to get confused when they're meeting this for the first time. Okay, so what would be this species here that results in this reaction?
Conjugate base.
Exactly, conjugate base. Very good. Whoops. CB. I'm going to see if I can keep track of who are answering questions so that I can see who's participating. Okay. Whoops. Okay. And then the other species would be what? The final product.
The conjugate acid.
Okay, very good. All right. So that's the answer for number 1A. Let's look at number 1B. So this would be, the first species here would be what?
An acid.
Okay, and the H2O would be the base, right? So what would this be? H3O plus.
The conjugate acid.
Exactly. And this would be, of course, the conjugate
Conjugate
base.
base.
Okay, very good. All right, last one. Now, this one is a bit tricky, but the same principles apply. All right. So what would you say this is? NaHCO3. Would that be the acid or the base in this reaction?
Base.
The base, exactly. And the HCl would be the acid, right? So the NaCl would be what?
Base,
Well, more specifically,
the conjugate base.
exactly. And the H2CO3 would be the conjugate acid. Now, strictly speaking, actually, the conjugate base would be actually the Cl minus, right? But since it has it combined with the sodium chloride, I'm just going to put Cb here. All right, and that's it. Okay, so that's basically number 1. Any questions about any of these? Any questions? Any questions? Okay, is it okay for me to clear this? Going
Yes.
on? Okay, me cleared. All right, so let's scroll down now to question number 2. Now, in this case, they gave you some compounds, some formulas, and you're to determine whether or not, you're to give the conjugate base in each case, right? So remember, the conjugate base is what is formed when a molecule or ion loses a proton, all right? So you have to ask yourself, what would be the formula of the result of a proton being lost by each of these? Excuse me. So what say you would be the answer to the first one?
The iodide ion, so I minus.
I minus is indeed correct. So hold on, I forgot to turn this on. Yes, so you are correct. I minus, very good. Okay, what about B, NH4 plus? What would be the formula of the substance formed when that loses a proton?
H3.
NH3 is indeed correct. And what about over here for C? What would be the conjugate base of that?
HCO3 negative.
Exactly, HCO3 minus. And what about the last one? D.
NO3 negative.
Exactly. Okay, very good. All right. Now, that's number 2. Number 3 says, give the conjugate acid for each of the following. So this is the opposite. In this case, you're writing down the formula of the substance formed when a proton is added to it. All right. So what would be the answer for A?
HCN.
HCN. What about B?
O negative.
Mm,
Or
Let
it
me
would be
see.
OH negative.
OH negative, exactly. OH negative. All right. And let me scroll down here. Whoops. Anyway, okay, let me just get rid of these here since I want to avoid confusion. Let me clear all drawing. Okay, so C. What's the answer for C?
CH3COOH.
I'm sorry?
CH3COOH.
Yes, that's indeed correct. COOH. And the last one, what would be the answer?
NH4 plus.
NH4 plus, exactly. All right. So it seems as if you guys have a good idea as to how to determine the conjugate base of an acid and vice versa. Okay, let me clear.
I have
all
a
this.
question.
Yes, ma'am.
On number 2, part B, why does it lose the positive sign?
Number 2, part B. Oh, because you're removing a proton. Now remember, a proton is H plus, right? So you're removing a hydrogen ion with a positive charge, right? So therefore, when you remove that, you're going to end up with NH3 with no charge because you're removing not only a hydrogen atom, but you're removing a positive charge as well.
Okay, thank you.
You see what I'm saying? Okay, good. All right, let me clear everything here. And let me scroll down. And now we're going to get into question number 4, which is more quantitative. Now they're asking about pH, which I don't think I discussed last time, but that would have been covered in the video, excepting that, as somebody just said earlier, the video wouldn't work. So let me just introduce to you briefly what we mean by the term pH. It's a rather simple concept. There's a pH scale that is used to measure the level of acidity of an aqueous solution. And the formula for calculating pH is pH is equal to minus log the concentration of H plus, or you can write it as minus log, the concentration of hydronium, which is actually more reflective of reality in terms of the presence of this in an aqueous solution, right? So that's basically what a pH is all about, right? And basically, you'll notice that there's a negative sign here, which indicates that the higher the concentration of the hydronium ion, the lower will be the pH, right? So basically what this is saying is that the greater the acidity of an aqueous solution, the lower will be the pH. So low pH corresponds to high acidity, and high pH corresponds to relatively low acidity, all right? There's also another term, POH, which is equal to minus log of the concentration of OH minus. So it's like the reverse of what we just said, right? And there's a relationship between these two, and that is given by, you know what, let me get out of this here. Let me clear this here and go to my writing tablet. Okay, so as I said before, the pH is equal to minus log of the concentration of hydronium ions. Whoops. Right, and the POH, write it here, is equal to the minus log of the concentration of OH minus, all right? And what you'll find is that there's a relationship between the hydronium ion concentration and the hydroxide ion concentration in any aqueous solution. So let me write this down. In any aqueous solution, the concentration of hydronium times the concentration of hydroxide is equal to a constant, which is called the ionic product of water, right? Which turns out to be equal to 1.0, I'm going to say 1.00 times 10 to the minus 14 at 25 degrees Celsius, all right? So this is another K equilibrium constant, because what they're talking about here is the auto ionization of water, right? You're going to have H0 plus times, not times, plus OH minus, all right? This is the equilibrium system for which this is the equilibrium constant. So KW is an equilibrium constant specifically applied to this equilibrium system. And the name given to this is called the ionic product of H2O, all right? So that's basically the relationship that you're going to need in order to establish a relationship between this and this. So as a consequence of that relationship, there are some other things we can write down. If we find the minus log of both sides, like this, that will be equal to minus log of KW, right? And if you remember anything from your log, from your algebra class, you know that log A times B is equal to log A plus log B, all right? So that means that this expression here can be said to be equal to minus log concentration of hydronium, put that in parentheses, plus minus log concentration of OH minus. And I'll put that in parentheses as well. And that'll be equal to minus log of KW, all right? So this part here will be equal to the pH of the solution, right? And this part here will be equal to the pOH of the solution. And minus log of KW would be the same thing as minus log of 1.0 times 10 to the minus 14, all right? Which would be equal to 14.00, all right? Because log of anything raised to the minus whatever would be equal to, well, to that number would be equal to that number. So basically, we have this relationship here as well that you're going to find very useful in your calculations for solving problems in this assignment, all right? So those are basically the relationships that you're going to need in this chapter. Now, another thing I want to mention has to do with significant figures, all right? When it comes to applying the log function. And to be perfectly honest, I'm not sure the reason why this is the case. Has to do something with algebra. I'm quite sure something you may know the reason why this is so. But whatever the number of sig figs here, when you apply the log to it, you have to round off your answer to the same number of decimal places. So like, for example, in this case here, you have 2 sig figs, right, represented here, which means that when you do the log of it, you're going to have 2 decimal places in your answer, right? So that's why I specifically wrote this down as 14.00, all right? Okay, so those are basically some of the things that you're going to need in this chapter, especially when solving the problems in this assignment. Okay, so before I leave this particular page, are there any questions? Any questions? Okay. So what I'm going to do now is go back to the PowerPoint. I mean, not the PowerPoint, the assignment. And now we're going to apply what we have learned to this question right here, which says, what is the pH of a solution that contains 25 grams of hydrochloric acid dissolved in 1.5 liters of water? Now, another thing I should mention, which you were introduced to in general chemistry, but will become more important here, is that there's a difference between strong acids and weak acids, right? In fact, let me go back to my writing part here. I should have covered that a while ago, but I forgot that you're going to need to know or be reminded of this. So I'm going to get rid of this here. Okay, so strong acids. Well, let me ask you this. What do you guys understand by that term, strong acid? When I say an acid is strong, what do I mean?
It dissociates 100%.
Okay, very good. So it undergoes complete dissociation, all right? And if you had me in Chem 1, I would have told you that you need to memorize these acids as strong acids. So for the benefit of those who have not had the privilege of being in my class, I'm going to let you know. These are the 6 strong acids that you need to memorize. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, what's the other one? Perchloric acid. And the last one is sulfuric acid. And let me just say something about sulfuric acid, which is a bit unique among these acids. You'll notice that each of these acids, except in the sulfuric acid, is monoprotic, which means that it has only one hydrogen here, right? That can be lost when it dissociates. In the case of sulfuric acid, you have 2 hydrogens here, right? So potentially you can have 2 dissociations where the first dissociation will look like this, H plus HSO4 minus, all right? And that dissociation is strong, all right? In other words, it undergoes complete dissociation to form H plus and HSO4 minus. However, the second hydrogen ion will undergo this, the conjugate base of the first step will undergo dissociation, but that dissociation is weak. So therefore, it will eventually reach equilibrium with the SO4 2 minus ion and the H plus ion, all right? So this dissociation is a weak dissociation, all right? The first dissociation is strong, but the second dissociation is weak in the case of sulfuric acid. So that's just something that you need to be aware of, all right? So basically, you need to remember these 6 acids as being strong acids. And if you're given any other acids, you can assume that those acids are weak. And we're going to talk about those later on. How do we deal with weak acids when it comes to the type of calculations involving, for example, determining the pH and so on. And while I'm at it, let me talk about the strong bases that you need to remember. Now, these are easier to remember because the strong bases are basically, let me just write it here. Strong bases, hydroxides of groups 1 and 2. All right? So I'm talking substances such as sodium hydroxide, lithium hydroxide, calcium hydroxide. These are all considered to be strong bases, all right? So pretty much any other bases that you'll encounter for all intents and purposes can be considered weak, all right? So it's very important that you identify and you can recognize strong acids and strong bases because that will become important as well later on. Okay, so let me go back to the question now. It says, what is the pH of a solution that contains 25 grams of hydrochloric acid dissolved in 1.5 liters of water, all right? So the first thing I would ask myself is what type of acid is this, right? And as I said before, hydrochloric acid is among the strong acids. So you know that it will dissociate completely to form H plus and Cl minus, all right? So this is what we need. We need to find the amount of H plus ions present in the solution in terms of moles. And because the dissociation is showing that there's a 1-to-1 mole ratio between the HCl and H plus, whatever the moles of H plus HCl is, that would be the same, right? So the way I set this up is that I start off with the 25 grams of HCl, and the first thing I would do is convert that to moles. So of course, that means you have to multiply by this conversion factor where we have 1 mole of HCl above, and below I'm going to have the molar mass, which is 36.46 grams, right? And that will give you the moles of HCl. Now, as I said before, there's a 1-to-1 mole ratio between the HCl and H+. So I'm going to put 1 mole of HCl down here and 1 mole of H+ above. And then I would divide that by the volume to get the molarity, which is given as 1.5 liters. So I'll put that down here, right? So basically what I've set up here is the way to calculate the concentration of H+, right? This will cancel with grams of HCl here. So this will cancel with that. This will cancel with that. And basically your answer will be given in M, or moles per liter. And according to my calculation, and please verify this because I could be wrong, but according to my calculation, this is equal to 0.46 M, all right? So that's the concentration of H+, but we're not finished yet because the question is asking for the pH. So the pH is now equal to minus log 0.46. All right. So when I did that calculation, the answer I got is 0.34. All right. So that's basically how that is determined. Okay, any questions about this? Any questions? Any questions?
There's no units after the pH, right?
Right, that's a very good question. Actually, yes, you're right, absolutely right. The convention is that there's no units associated with pH or POH or any of the P's that you're going to meet, because there's some other P stuff that you're going to meet. You're going to meet pKa, pKb, pKi. So any of those P's that you're going to meet, there are no units associated with them. And I just, oh, I'm sorry, go ahead. Mm-hmm.
And when you're setting up this equation for the volume on the bottom, does that always have to be in liters?
Yes, ma'am, because remember,
Okay.
molarity is expressed in moles per liter.
Moles over liters, that's
Exactly,
right.
exactly. So
Right.
the liter
Thank you.
unit is very important there. I just remembered something that I neglected to mention. So let me quickly do that before I forget. Going back to the pH here. So let me go back to my writing pad here, and let me hold on. Let me clear this, and let me get out of this, and let me get rid of this. Okay, and that is going back to the relationship between pH and POH. Remember I said that pH plus POH is equal to 14.00, all right? So basically, there are several situations that can occur in an aqueous solution when you're looking at the relationship between the pH and POH. In a neutral solution, right, pH will be equal to POH, all right? And correspondingly, the concentration of H+ will be equal to the concentration of OH-. Whoops, writing too fast. Let me erase this here. And let me go back to here and set this to be equal to the concentration of OH-, right? So in a neutral solution, like for example, pure water, the concentration of H+ and OH- will be the same, which means that the pH is equal to POH. Now, if that's the case, based on this equation here, assuming that the sum of the pHs is equal to 14.0, that means that the pH, which is equal to the POH, what am I doing? The pH, which is equal to POH, will be equal to 7.00, right? Which means that this will be equal to 1.0 times 10 to the minus 7 M, all right? So that's what happens in a neutral solution. Now, in an acidic solution, the pH is less than 7, which means that the POH would be greater than 7, all right? Correspondingly, what that means is that the concentration of H plus would be greater than the concentration of OH minus, all right? So that's what happens in an acidic solution. And then finally, in a basic solution, the reverse is true. In other words, the pH would be greater than 7 and the pOH would be less than 7, which means that the concentration of H plus would be less than the concentration of hydroxide ion, all right? And this is very important for you to understand, because one mistake that students sometimes make is that they assume that because a solution is acidic, that means it has no hydroxide ions. That's not true, right? What the term acidic means is that the concentration of H plus is greater than the concentration of the hydroxide ions. And the opposite is true for a basic solution, all right? And let me also say that we can actually measure the pH directly. There are two main ways of doing it. The least accurate way, or the less accurate way of doing it, is by using indicator papers. Basically, these are strips of paper which have which are basically soaked in a particular pigment, which gives different colors under different acidic or basic conditions. These are not the most accurate, but they're useful for approximate purposes, all right? We call them pH papers or indicator papers, all right? And then we have what are known as pH meters. And pH meters are, as they sound, basically electronic instruments, which has, as a part of the setup, an electrode connected to a panel, which gives you a pH reading. And basically what you do is dip the electrode into the solution and the pH reading comes out. That's more accurate. Typically, they are expressed to 2 decimal places in terms of the pH units, all right? So that's just giving you some background as to how we actually measure the pH. Okay, so let me go back to the questions. All right, so we just did question number 4. So let me see here. How would you do question number 5? Let's hear your ideas, because if you understood what we did in question number 4, you should be able to do question number 5. So question number 5 says, what is the pH of a solution that contains 1.32 grams of nitric acid dissolved in 750 mils of water? Okay, so let's hear your suggestions.
You need to get the grams of nitric acid into moles of nitric acid.
Okay, so 1.32 grams of nitric acid, HNO3. We convert that to moles. So how do we do that?
You use the molar mass.
Yep. Let me get rid of this thing here. Okay. So up here, you're going to have 1 mole of HNO3. And I think I calculated, let me see over here. I think I calculated the molar mass of nitric acid, which is 63.01 grams. That goes here, 63.01 grams of HNO3. Okay, what's the next step?
We have to figure out the equation, or like to see the mole ratio.
Okay, so HNO3 dissociates to form H plus and NO3 because it's a strong acid, right? And again, that should be actually the first thing you ask yourself. What kind of acid is it? Is it strong or weak? And we know it's strong. Okay, what's the next step?
You would set up the molar ratio to cancel out the HNO3.
Okay, so I think what you mean is that I put 1 mole of HNO3 down here, right? And 1
Yes,
mole
sir.
of H plus above. Very good. What's the next step?
You need to convert the 750 milliliters into liters.
Okay, I would do that down here because remember, eventually you have to divide the moles by the volume, right? So 750 mils, convert to liters, 1 liter over 1,000 mils. And that's the setup. The grams of nitric acid will go, the moles of nitric acid will go, the milliliters will go. So your answer will be in M when you do that. And when I did that calculation, I got 0.028 M. So how do we find the pH?
The negative log of that number.
Okay. And according to my calculations, when I did that, the answer becomes 1.55. And that's how you do that. All right. Okay. Any questions about this one? Any questions? Any questions? All right. Let me clear this. Or can I clear this? I mean,
Yes.
all right, let me do that. Okay, so scrolling
Real
down.
quick,
Oh, yes, ma'am.
when you put the answer after the equation, like the 0.028 m, would you
Mhm.
not put that over liters because liters doesn't cancel out?
Well, the M, let me show you something here. The M is the same thing as moles per liter. So whenever you see uppercase M, like this, as a unit, that's the same thing as moles over liter. So when we did all that calculation, I wish I didn't, that's why I keep asking you guys if it's
No,
okay
it's
to clear.
okay. It's all right that you erased it. I'm just asking.
Right,
So it would be inaccurate if you put M over L. You would have to put moles over L
exactly,
for it to be
exactly,
accurate. Okay.
exactly, absolutely right, yeah. Mhm. Okay, so let me clear this now. And let me scroll down. Okay, I want you to think about this one. This one is a bit different from the others that we looked at because in this case, we have two acids in the same solution. So let me hear how you approach this one.
I would start by setting up a formula.
Okay, okay. So in other words, write down the equations, right? For the
Yes.
okay. So let me okay, let me write it here. So for hydrochloric acid, that dissociates to form H plus and Cl minus. And for the nitric acid, that dissociates to form H plus and NO3 minus. Okay. What next?
Do we find the molarities now?
Okay, so well, they didn't give you the molarity of each. They gave you, well,
Yeah.
you're right. You're going to find the molarities, but look at what they gave you. They gave you 1.2 moles of nitric acid and 1.7 moles of the hydrochloric acid, right? So how would you use those two to determine the molarity of H plus? Because that's ultimately what you want to find, right?
Moles divided by liters.
Okay, so what would be the mole value that you're going to use? Because they gave you two mole values. They gave you 1.2 and they gave you 1.7.
Would you add them together?
Absolutely right. 1.2 moles plus 1.7 moles because they're in the same mixture, right? So basically, the moles of H plus from the acid, from the hydrochloric acid, would be the 1.7, and the moles of H plus from the nitric acid would be the 1.2. And then you divide that total by the volume, which is 1,000 liters, 1,000 liters, right? So this, according to my calculation, gives, okay, I think I have this incorrect in terms of rounding off. Since this is 1 sig fig here, I'm just going to round this off to 3 times 10 to the minus 3, and this would be M, all right? So the pH will be equal to minus log of 3, all right? So I need to do this calculation here because the answer I have worked out earlier is not 100% correct. So 3 log Okay, so hold on. Hold on, wait a minute. Oh, I'm sorry. Made a mistake, a big boo-boo. And that should be 3 times 10 to the minus 3. Okay, so let me see what that gives. Final log. Okay, so according to my calculations, this would be equal to 2.5. And that would be the answer. All right. Okay, any questions about this one? Any questions?
Yeah, I had one question about it.
Mm-hmm.
For the other ones, you did the mole ratio as 1 to 1, but
Mhm.
does this one not have 2 moles of H plus?
No, okay, I understand what you're saying. What you need to recognize is that each reaction, each dissociation produces 1 mole of H plus, right? Now,
Yes.
in the case of the nitric acid, it produces 1.2 moles, right? So that's one result from one dissociation. And then in the case of the hydrochloric acid, that produces 1.7 moles. So you see, what you have to understand is that the moles of acid, the moles of hydrochloric acid is not the same as the moles of nitric acid. You see what I'm saying? So you have to calculate or figure out the amount of H plus that would come from each dissociation.
Okay, gotcha. Thank you.
You see what I'm saying? And then, so that's why we say 1.2, that comes from the nitric acid, 1.7, that comes from the hydrochloric acid, and then we add them together and divide by 1,000. And that's how we get the total hydrogen ion concentration, and then we find the minus log of that, and that is the answer. Okay. Any other question before I move on from this? Any other questions? All right, next question. You should be able to answer this based on what I said earlier. It says, if a solution has a concentration of H plus of 4.5 times 10 to the minus 7, is this an acidic or basic solution? And it says explain. So let's hear your thoughts on this one. The concentration of H plus is 4.5 times 10 to the minus 7. Now, let me ask. Oh, let me
I
hear
would
your
say
answer.
it's very acidic.
Okay, and you say that because?
If you work out and get regular notation for the 4.5, it's very much smaller than 7.
Okay, your answer is right, but your explanation is wrong. Because, and here's where you went wrong. Let me try to explain it right here. Here's where you went wrong. You're correct. It is acidic. So let me write that down first, right? But what you're doing, or what you have done, is compare this value, which is the concentration of H plus, to the pH for a neutral solution, right? You're not comparing the concentration to the pH. You're comparing the concentration of H plus in this solution to the concentration of H plus in a neutral solution, which is 1 0.00 times 10 to the minus 7, right? This is what you're comparing. You're comparing this to this value, right? And as you can see clearly, 4.5 times 10 to the minus 7 is greater than 1.00 times 10 to the minus 7. So therefore, for that reason, the H plus concentration is, I'm sorry, the solution is acidic. All right?
I have
Any
a question?
Yes, ma'am.
Could you take the negative log of that number and compare it to 7?
You could just as well do that. In fact, let's do that now. So based on this, the pH would be equal to 4.5 times 10 to the minus 7, and then I do the minus log. So I got 6.3 here, right? In fact, to be more precise, 6.35, right? That would be the pH. If you do the minus log of this, this is what you're going to get. If you do the minus log of this, the pH is going to be equal to 7. 0.00, right? Obviously, 6.35 is less than 7. So therefore, again, because the pH is less than 7, that means that the solution is acidic. So either explanation would work, actually. All right? So this is just an example of, using two different ways of explaining the same thing, and the result would be the same. Okay, any other questions about this? Any other questions? Any other questions? Okay, so let me clear this here. And let me scroll down. Okay, okay, this is an interesting one. Number 6, it says an acidic solution has a pH of 4. If I dilute 10 mils of the solution to a final volume of 1,000 mils, what is the pH of the resulting solution? So let me hear your ideas about this one. How would you solve this particular one? This has to do with dilution. And you should recall a very important equation when it comes to dilution. What's the dilution equation? Can anybody tell me? There's an equation that you use to calculate the concentration of a more dilute solution made from a more concentrated solution.
M1V1 equals M2V2.
Exactly. M1 V1 is equal to M2 V2. I like to use C1 V1 is equal to C2 V2 because C1 and C2 can be expressed as molarity or any other forms of concentration, but either will do. Okay, so based on that, and based on what we just learned about pH, how would you tackle this problem?
I could be completely wrong here, but I'm thinking maybe get
Why-
the
why-
negative
why
log
start
of
also-
4.
Why are you starting also negative? Come on.
Maybe the negative log of 4.
Okay, so the pH is equal to minus log of the concentration of H plus, right? But what you want to find is the concentration of H plus. So what is that equal to? Can anybody tell me?
Negative log of 4.
If the pH is equal to minus log of H plus, then what is concentration of H plus equal to?
10 to the 4th,
Actually 10 to the,
negative 4.
well, based on this equation here, 10 to the minus pH. And since you said the pH is equal to 4, that means that concentration of H plus would be 10 to the minus 4 M, all right? Okay, so if that is true, what next?
That's the initial molarity.
Okay, that would be, okay, very good. So that will be M1, right? Okay, what next?
You would multiply it by the initial volume.
Okay, so in other words, you're going to use this equation right here, right?
Yeah.
Now, ultimately, what you want to find is this, right?
Yes, we're trying to find M2.
Okay, so what I'm going to do is solve for M2. M2 is equal to M1 V1 over V2. So M1 we identify as 10 to the minus 4. And V1 is what?
And milliliters.
10 mils. Okay, and what is V2?
1,000 milliliters.
Okay. And what does that give? Let me see if I have the answer here.
I have a question. Are you supposed to convert those to liters though?
Don't have to. You know why? They will cancel out.
Okay.
Very important question you asked. You see, whenever you're using this equation here, or this equation, M1 V1 is equal to M2, it does not matter what the units are for M1 V1, M2, or V2. However, the units must be the same on both sides. You see what I'm saying? So the units for M1 must be the same as the units for M2. The units for V1 must be the same as the units for V2.
Okay, thank you.
All right. Okay. So what
I'm
does
a
this give?
little confused with
Yeah.
the wording of this
Okay.
because I feel like wouldn't you take 1,000 minus 10 and get the initial volume because it says the final volume's 1,000?
Well, look at how the question is worded. The question says, if I dilute 10 mils of this solution to a final volume of 1,000 mils. You see what I'm saying? So you're starting off with 10 mils of the original solution, right? And you're adding water until the final volume is 1,000 mils. Right? So the initial volume is 10 mils and the final volume is 1,000 mils. So the final volumes wouldn't be 1,000 minus 10. It would just simply be 1,000 mils. All right. Okay. So let's see, what does this give? According to my calculations, this works out to be equal to 1 times 10 to the minus 6 m. Okay, so what do we do with that number?
You calculate pH using the pH
Okay,
equation.
so pH would be equal to minus log of 1 times 10 to the minus 6, which works out to be equal to 6.0. All right, and that's how that is done. Okay, any questions about this? All right, I'm going to take the first break here. I'm over my 50-minute usual break. Okay, so we'll get back at 11 o'clock, all right? Okay, folks, I am back and we're going to continue, unless there are any questions you guys have to ask, but I'm just going to continue with the assignment. And we stopped at question number 6, all right? Excuse me. Okay, so let's look at question number 7. And in the case of question number 7, you're given a series of solutions and you're asked to find the pH in each case. Okay, let me share my screen. I keep forgetting. And let me, okay, so question number 7, right here. And it's asking for you to determine the pH of these solutions. And first of which is a solution that is 4.5 times 10 to the minus 3 molar HBr. All right. Okay, so any ideas how to deal with this one?
We would write the equation for HBr dissociation and figure out that the ratio is 1:1,
Okay.
and then plug it into the pH.
Okay, so whatever the concentration of this is, the concentration of H plus is the same, right? So the pH would be equal to minus log of 4.5 times 10 to the minus 3. And according to my calculation, this works out to be equal to 2.35. 2.35, and that would be the answer. So that's a relatively simple problem. Now, this one is slightly more complicated because in this case, they're asking for the pH of a 3.67 times 10 to the minus 5 m potassium hydroxide solution. So let me hear what your suggestions would be for this one.
We would do the same thing, but find pOH of the OH ion. And
Okay,
then
hold on.
convert.
So this is the dissociation, right? And then you're saying what now? Find what?
There's still a 1:1 ratio,
Right.
but we use OH negative to
Okay.
find pOH.
Oh, so find pOH. So pOH would be equal to minus log of 3.67 times 10 to the minus 5, all right? So I think I did that, and I got 4.4. What next?
You would do 14 minus the pOH would equal pH.
Okay, so the pH would be equal to 14.00 minus the pOH, which we just calculated. So that's 14.00 minus 4.44. And according to my calculations, that becomes 9.56. And that's it. That's how that is done. All right. Okay, any questions about that? Any questions? All righty. Is it okay for me to clear this?
Yes.
All right, let me do that. Let me do this. Let me scroll down. Okay. This one says a solution made by diluting 25 mils of a 6.0 m hydrochloric acid until the final volume of the solution is 1.75. So, any ideas about how to deal with this one?
We use
We would use the M1V1.
Okay, so let me write that equation down here. Oops, I need to turn on this again. Okay, so the equation you're going to use is M1 V1 is equal to M2 V2. Okay, so far so good. What will be the next step?
You need to change the 25 ml to liters.
Okay, that will be the V1, right? So this would be the V1. This would be the M1. And you're saying that you convert the 25 mils to liters. I would agree with that. So let me write down this first. Well, let me do this first. You want to find out what M2 is, right? So M2 will be equal to M1 V1 over V2. So basically to find M2, we're going to need M1, which is 6.0 M, uppercase M, multiplied by the 25 mils. And as you correctly said, you need to convert that to liters. So you would multiply this by 1 liter over 1,000 mils. All right. And then you divide that by V2, which is the 1.75 mils. So the milliliter units will cancel out. The liters, oh, this should be 1.75 liters, I'm sorry. So the milliliter units will cancel out, the liters units will cancel out, and then you can get the final answer, which according to my calculation works out to be equal to, okay, so the answer I got is 0.086. 0.086 M, all right? And then what do we do with this?
Plug it into the pH equation.
Okay, so pH will be equal to minus log of 0.086. And what does that give? According to my calculations, I got 1.07. So that would be the final answer. All right. Okay, any questions about this one? Any questions? Any questions? Okay, is it okay for me to clear this?
Yes.
All right. Scrolling down. Okay, I want you to look at this one and tell me what you think you would do with this. It says a 5 liter of an aqueous solution that contains 1.0 grams of HBr and 1.0 grams of nitric acid. So you're asked to find the pH of this solution.
You would convert the grams of both to moles of both and then add them and then
Okay.
divide by the liters to get molarity.
Yeah, that's pretty much it. You're absolutely right. So let me start off with the 1.0 grams of HBr. And as you correctly said, we have to convert each of them to moles. Now, in the case of HBr, the way we do that is we divide by 80.91 grams of HBr. And according to my calculation, this works out to be equal to 0.012 moles, whoops, of HBr. And then we do a similar calculation with the nitric acid. Multiplied by 1 mole of HNO3. And down here, the molar mass, which is 63.01 grams of HNO3. And according to my calculations, that works out to be equal to 0.028 moles of HNO3. And then we add these together. And when I did that, oh, wait a minute, my mistake. This is not correct. This should be 0.016. And then when you add them together, you get a 0.028 moles of HNO3 of total. Let me just put total here, all right? Okay, and then as you correctly said, this would be equal to the concentration of H plus because they are both strong acids. HBr and nitric acid are both strong acids. So therefore the concentration, or actually this should be the moles of H plus. So the concentration of H plus would be equal to the moles of H plus, which is 0.028 moles divided by the volume, which is 5 liters. And according to my calculation, this works out to be equal to 6 times 10 to the minus 3 m. So therefore, the pH would be equal to minus log of 6 times 10 to the minus 3. And according to my calculation, this works out to be equal to 2.2. And that's how that is done. All right. Any questions about this one? Any questions? Okay. Can I clear this?
Yes.
All right, now we're going to get into some interesting situations because the next question has to do with weak acids. All right, so let me clear this. So before I get into the next question, oh, wait a minute. Oh yeah, this is it, right. Let me talk about weak acids for a minute. Again, this is something that you should have covered by yourself in the video lectures, but just in case you missed some important details, let me talk about weak acids. So we talked about strong acids already. They undergo complete dissociation. Weak acids, on the other hand, undergo partial dissociation. So basically, if you add a weak acid to water and it dissolves, then eventually what's going to happen is this equilibrium right here, right? You're going to have the back and forth, and we can write down an equilibrium constant. We call it Ka, and that will be equal to the concentration of H plus times the concentration of A minus divided by the concentration of HA, right? And what you'll find is that typically these numbers are relatively small. They can go from anywhere from 10 to the minus 4 to even less values. You can have something 10 to the minus 10, for example, of the order of 10 to the minus 10. So, you know, those are the kind of values that you can observe when it comes to determining the equilibrium constant. And this, by the way, this equilibrium constant is called the acid dissociation constant. Acid dissociation constant, all right? So basically that's pretty much, there's some more things involved. In fact, you're going to see that, that involvement in question number 8. But this is pretty much the essentials that you need to at least start solving problems involving weak acids. You need to recognize that weak acids, the type of calculations that you'll be doing will be a bit different, and it's a bit more complex compared to the strong acids, because in the case of the strong acids, you can pretty much assume that whatever the molarity of the original acid is, the molarity of the H plus will be the same. You can make no such assumptions about weak acids because they undergo incomplete dissociation, all right? So with that said, let me go back to the question here. And it says that the pH of 0.065 m solution of formic acid is, the pH is what you need to find. I'm sorry, I'm not reading the question correctly. You need to find the pH, right? They gave you the acid dissociation constant, which in the case of formic acid is 1.8 times 10 to the minus 4. Okay, so that's a question. So how are we going to solve this? All right, well, basically what you'd have to do is set up something that we saw before in the previous chapter, and that is an ice table. So the first thing I'm going to write down is the equation for the dissociation of the weak acid. And I'm just going to use HA. I don't need to write down the formula, the entire formula of the formic acid. So I'm just going to use HA to represent the formula for the acid, all right? So that's the initial, that's the equation. So you're going to set up an ice table, as I said before, where we have initial, change, and equilibrium. All right. So initially, the concentration of the formic acid would be 0.065 m. Here, before anything starts, you're going to have 0 and 0. The change here, we don't know what it is, so we're going to call it minus x, where x represents concentration of HA reacting. All right. Now, if minus x is a change in concentration of HA, then the concentration change for H plus will be plus x, and the same is true for A minus plus x. And that's because of the stoichiometry. It's a 1-to-1-to-1 ratio between the HA, the H plus, and the A minus. So whatever the moles of this reacting, the moles of these two produce will be the same. So at equilibrium, the concentration of HA would be 0.065 minus x, while that of H plus and A minus would be x and x respectively. So now we can write down the Ka expression for the weak acid, which would be the concentration of H plus times the concentration of A minus divided by the concentration of HA. And then we can plug in these terms, these terms into this equation. So we're going to have x for the concentration of H plus at equilibrium times x, the concentration of A minus, and for the HA is going to be 0.065 minus x. So we can actually simplify this to x squared over 0.065 minus x. All right. Okay. So at this juncture, in order to simplify things a bit, make life a little bit more, or I should say, well, more convenient, we can make an assumption here. And this assumption is based on the fact that the acid that we're working with is a weak acid. Now, if HA is a weak acid, you'd expect that the value for X would be very small, especially when compared to the initial concentration of the weak acid, right? Which is 0.065 m, right? Now, I don't know if you guys are familiar with this symbol from math, right? It looks like 2 less than sign. What that means basically is that X is very, 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 very small compared to 0.065, right? Now, if that is true, if X is very small compared to 0.065, that means that 0.065 minus X can be approximated to be equal to 0.065. Because what we're saying here is that X is so small that it's effectively 0, and therefore, when it's subtracted from 0.065, you're going to end up with 0.065 anyway, all right? So based on that assumption, then we can say, we can simplify this equation. I'm going to write it down here. Ka is equal to x squared over 0.065. And then we can rearrange this to solve for x, which is equal to the square root of Ka times 0.065. And then we plug in the values. So the question gave you that Ka is equal to 1.8 times 10 to the minus 4 times 0.065, and we find the square root of that, all right? And when I did that, I got 3.4 times 10 to the minus 3 m, all right? So that would be X, which would be equal to the concentration of H plus, all right? Okay, now, one would be tempted to just go ahead and find the minus log of that to get the pH, all right? However, that would not be advisable, not be appropriate. And the reason why is because of the assumption that we made here, right? Remember, we made the assumption that X is small compared to 0.065. Now, what we have to do next is that we have to test the assumption to make sure that the assumption is valid. If the assumption is valid, then we can go ahead with what we calculated for the concentration of H plus and find the pH based on that. However, if the assumption is not valid, then we have to go back to this expression right here and solve it the long way. In other words, without assuming that X is very small. So the question is, how do we test the assumption of this? Well, firstly, in order to answer that question, I need to clear what I have here. So let me ask you, is it okay for me to clear this now? Because I need some space. I need some more space.
Yes.
Okay, so let me clear this now. So how do we test the assumption? Well, there's a thing called percent dissociation that we need to calculate. So let me tell you what percent dissociation is. Percent dissociation, and this can apply to weak acid and weak bases, but in the case of weak acids, the percent dissociation of a weak acid would be equal to the concentration of H plus at equilibrium divided by the initial concentration of the acid that you start off with times 100%, right? So that would be the percent dissociation. Now, let me just put something here next to it. If the percent dissociation is less than 5%, then the assumption is valid. So that's a criteria that we're going to use to figure out whether or not the assumption we made earlier is a valid assumption. We have to calculate the percent dissociation and compare it to 5%. If it's less than 5%, then the assumption is valid. Okay, so let's do that. Now, based on what we did before, the concentration of H plus is equal to 3.4 times 10 to the minus 3 m, and the initial concentration of the acid is 0.065 m, and then we multiply all of that by 100%. And when I did that, the answer I got is 5.2%. So what that tells me is that the assumption is not valid. All right. So what does that mean? That means we have to go back to this equation right here. 1.8 times 10 to the minus, oops. Okay, oh Lord. Let me do this again. Okay, 1.8 times 10 to the minus 4. That is equal to x squared over 0.065 minus x. So we have to keep the value or the term x here. We cannot assume, therefore, that x is small like we did before. So basically what it comes down to is solving this equation here. Now, I'm not going to go through all the steps. I'm just going to show you the result of this in terms of the quadratic equation that you're going to end up with. So if you rearrange this to get the quadratic equation, what you're going to get is x squared plus 1.8 times 10 to the minus 4 x minus 1.2 times 10 to the minus 5, and that will be equal to 0, all right? So basically, this is the quadratic equation that you need to solve. And if you solve this, you're going to get two possible values of x. One possible value of x would be 0.0034, and the other possible value of x would be 0.0036 minus 0.0036, all right? So which one we're going to use? We're going to use this one because you cannot have a negative concentration. So this will be equal to the concentration of H plus, and therefore to find the pH, that will be equal to minus log of 0.0034, and according to my calculation, that works out to be equal to 2.47. And that's how you do that, all right? So as you can see, calculating the pH of a weak acid can be, well, definitely is more complicated than calculating the pH of a strong acid, all right? Because again, as we said before, you cannot assume 100% dissociation for a weak acid, as you did in the case of a strong acid. So therefore, you have to go through all the steps that I just went through in order to do that type of calculation, all right? Okay, any questions about this one? Any questions?
I have a question.
Yes, sir.
So the assumption wasn't valid, right? Because the percent dissociation was greater than, or the
Right,
percent was
right.
greater than 5, right? But, and then we went through and did the whole thing with
Uh-huh.
the quadratic equation. And then we
Mhm.
ended up getting the same number we got with our assumption.
Yeah, exactly. And sometimes that happens. But basically, what I would recommend you do is that if the assumption, if the, not the assumption, I'm sorry, if the percent dissociation is greater than 5%, just go ahead and do it the longer way, because there's no guarantee that the answer is going to be the same as what you would have done if you have not, if you have made the assumption. You see what I'm saying? So in this case, it works out to be the same, but in other instances, I'm quite sure you'll find that that's not going to be the case.
Okay.
Yeah. Okay, any other questions about this particular problem? Any other questions? Okay, is it okay for me to clear this?
Yes.
All right, so let me clear that, do this, and scroll down. Okay, so the question is asking for you to compare the pH of the following. So basically, you're to calculate the pH of each of them, and I guess compare, which one is greater or lesser. I can tell you straight off the bat that, for example, in this case here, in the case of A, where you have 0.10 M nitric acid, which is a strong acid, and then you have 0.10 M nitrous acid, which is a weak acid, I can tell you that the pH of the nitric acid is going to be lower for the same molarity, right? Because nitric acid is strong, nitrous acid is weak, all right? But the question is asking for more than that. It's asking for you to compare the pH. So I guess you need to find the pH of both acids and compare them. All right. So let me go to my writing thing again. So let's find the pH of nitric acid. How would you find the pH of nitric acid? So I'm just going to write here for HNO3. How do we find the pH?
You can write the equation to find out it's a 1-to-1 ratio and then plug
Okay.
in the pH equation.
H plus NO3 minus, right? Which means that it's a 1-to-1, right? As you said, so pH in this case would be equal to minus log of 0.10, which will be equal to 1. 1.00. That will be the pH of that solution. All right. Okay, what about for the nitrous acid, HNO3? So in this case, the nitrous acid is a weak acid. So in other words, it undergoes partial dissociation as reflected in this equation right here. Right? So how would you go about doing this? And you should be able to do this now based on what we did in the previous question.
You would set up the ICE table.
Okay, set up the ICE table. So initial, change, equilibrium, right? Okay, so initially you would have none of these two, right? And you would have 0.10 here, right? So what's the next step? What goes in this row right here?
The change, so under
Mhm.
HNO2 would be minus X
Minus X, and this would be
plus X.
plus X. Whoops, something is wrong with my tablet here. I don't know exactly what it is. Okay, so plus X here, and plus X here. Okay, what next? So down here, you're gonna have 0.10 minus X. You're gonna have X here, you're gonna have X here. Okay, what's the next step?
You plug that into the Ka equation.
Okay.
So it ends up being X squared over 0.1 minus X.
Okay, very good. But just to, make sure that everybody understands what's going on, I'm just gonna write down oh, by the way, this should be NO2, not NO3. So this should be NO2 minus over HNO2. And as you correctly said, you're going to get X squared over 0.10 minus X. And that would be equal to Ka, which is 4.5 times 10 to the minus 5. Okay, so what's the next step?
We make the assumption that
Okay,
X is like nothing because K is very small.
right. So we assume that X is so small compared to, what is it, 0.10? So therefore, that means that 0.10 minus X is approximately equal to 0.10. So basically, that would simplify this equation to X squared over 0.10, and that would be equal to 4.5 times 10 to the minus 5, which means that X squared, or X would be equal to the square root of 0.10 times 4.5 times 10 to the minus 5. And when I did that calculation, the answer I got is, oh, I didn't do that. Okay, let me do this here. 4.5 times 10 to the minus 5. 4.5 times 10 to the minus 5 times 0.1 equals that, and then I found the square root of that. So the value for X I got is 2.1 times 10 to the minus 3. Let me do this again just to make sure I did this right. 0.1 times, oh, no. Oh, yes, okay. 0.1 times 4.5 times 10 to the minus 5. And then I find the square root of that. Okay, so this is what I got, 2.1 times 10 to the minus 3. Okay, so what's the next step? I'm gonna need some space. Let me erase up here. Okay, so what's the next step? I'm going to continue up here.
You have to do the %i to check the assumption.
Okay, so percent dissociation. All right, and that would be equal to, in this case, 2.1 times 10 to the minus 3 divided by 1.10 m times 100%. So let me see what that gives. Divide by 0.1 times 100. Okay, so in this case, it's 2.1%. Okay, so that is definitely less than 5%, right? So therefore, the assumption is valid, which means that we can set this to be equal to the concentration of H0 plus, which means that the pH of the solution will be minus log the concentration of H0 plus minus log of 2.1 times 10 to the minus 3. So 2.1 times 10 to the minus 3. If I find a log of that, the answer turns out to be 2.68. And that's basically how that is done. And then you compare the 2.68 to the 1.0 that we got earlier. And obviously 1.0 is less than 2.68, which means that the nitric acid is stronger than the nitrous acid. All right. Okay, any questions about this? Any questions? Any questions?
No.
All right, can I clear this?
Yes.
All right. Let's continue down. Okay, now this one is a bit different. It's asking for you to compare the pH of these two solutions. One of them is potassium hydroxide, 0.02 m, and the other one is ammonium hydroxide, 0.10 m. And I would expect that the one that would have the higher pH would be the potassium hydroxide, because it's a strong base and the ammonium hydroxide is a weak base. All right. Okay, but again, we have to calculate the pH in each case. So let's start off with the potassium hydroxide. So what's the first step? How would you determine the pH of potassium hydroxide? Anybody?
You write out the equation to find the 1-to-1 ratio and then plug it into the pH equation.
You sure about the pH equation?
Just kidding, the OH,
Hmm?
and then you'd use the OH equation and
You mean-
then.
You mean POH, right?
Yeah,
So POH would be equal to minus log of 0.02, right? And that is, according to my calculations, equal to 1.7. So therefore, the pH of this solution will be equal to 14.00 minus 1.7. So 14 minus 1.7. And according to my calculations, this works out to be equal to 12.3. So that's the pH for the, so this is for the potassium hydroxide. So we have to do a similar calculation for the ammonium hydroxide. Now, this one is a weak base and it's very similar to what we did for weak acid. In this particular case, the equation would be NH4 plus, I'm sorry, NH4OH dissociating to form NH4 plus OH minus, right? So again, we're going to set up an ice table. Initially, you're going to have 0.10 for the ammonium hydroxide. You're going to have 0 here, 0 here. The change here is going to be minus X plus X plus X. So at equilibrium, you're going to have 0.10 minus X, excuse me, and then you're going to have X here and X here. So the Kb expression is going to be equal to concentration of NH4 plus times the concentration of OH minus divided by the concentration of NH4OH. And then we put in the terms. You're going to have X squared here over 0.10 minus X, right? And then as we did before, we're going to make an assumption that X is very small compared to 0.10. So that means that 0.10 minus X is approximately equal to 0.10. So therefore, this would be simplified to X squared over 0.10. And that is equal to Kb. And the Kb value that they gave is this. So I'm just going to set that right here, 1.8 times 10 to the minus 5. So we need to, this should be X squared here. We need to solve for X. I'm going to erase this line here and continue up there. So basically, after rearranging, you're going to get X is equal to the square root of 1.8 times 10 to the minus 5 times 0.10. And then we solve for X. According to my calculations, X is equal to, hold on, let me do this here, 1.8 times 10 to the minus 5 times 0.1. And then I find the square root of that. So I got 1.3 times 10 to the minus 5, 10 to the minus 3, I'm sorry. All right. And then I find the percent dissociation. Let me do that here. Percent dissociation will be equal to 1.3 times 10 to the minus 3 m divided by the initial concentration of the ammonium hydroxide, which is 0.1, 0 m times 100%. So let's see what that gives. 1.3 times 10 to the minus 3 divided by 0.10 times 100. And according to my calculations, this works out to be equal to 1.3%. So assumption is valid. Assumption is valid. So that means that this value here, we can set that to be equal to the concentration of OH minus. Okay, so now that we have done that, what will be the next step? Let me erase down here. Okay, so now that we have determined the concentration of OH minus, what will be the next step?
Plug it into the POH equation.
Okay, so that would be POH is equal to minus log of 1.3 times 10 to the minus 3. And let me see what that gives. So 1.3 times 10 to the minus 3. We find the log of that, minus log of that. Okay, so according to my calculation, this works out to be equal to 2.89. In fact, this should be 2.89 would be the POH, and therefore the pH is equal to what? What is pH equal to?
14 minus 2.89.
14.0 minus 2.89. And as a result of that, I got 11.11. That would be the final answer. All right. Okay. Any questions about this one? Any questions? Oh, we're not finished yet because it says compare the pH to the previous one. So the pH we got here for the ammonium hydroxide is 11.11. And the pH that we got originally was what? For the potassium hydroxide, 12.3, right? So for the potassium hydroxide, we got 12.3. For the ammonium hydroxide, we got 11.11. So therefore, we know which one is, what did the question ask for? The question asked, compare. All right, so basically we can say that the potassium hydroxide has a higher pH compared to the ammonium hydroxide. So that's basically how that is done. All right. Okay. Any questions about this one? Any questions? Any questions? Okay, let's see here. Is it okay for me to clear this?
Yes.
All right. Consider it cleared. All right, so let's move on to number 10. So number 10 says you have to calculate the percent ionization of, and basically percent ionization is the same thing as percent dissociation, all right? Okay, so since we have done some of that in the previous question, you should be able to do this one. So let me hear what you have to suggest. How would we solve this particular problem?
You'd start by writing out the equation.
Okay,
fix
so,
The ratio.
okay, so in the case of this, right? Another question you have to ask yourself is what kind of acid is it? And the hint is right here. So a weak acid. Whenever they give you the Ka value for an acid, you can pretty much assume it's a weak acid, all right? So I'm just going to use HA here. In fact, let me do that down here. HA dissociates as a weak acid to form H plus and A minus. All right, let me erase this here. Okay, so what's the next step?
Base table.
Okay, so initially you would have 0.015, 0 here, 0 here. The change here would be minus x, minus x, plus x, plus x, all right? So at the end, at equilibrium, you're gonna have 0.015 minus x. Here you're gonna have x, here you're gonna have x, and then we write down the Ka here, which is equal to x squared over 0.015 minus x, and that would be equal to Ka. And then we make our assumption that x is very small compared to 0.015. So that means that 0.015 minus x is approximately 0.015. So Ka would be equal to x squared over 0.015, which means that x would be equal to the square root of Ka times 0.015. So that means that x would be equal to the square root of Ka, which is 1.8 times 10 to the minus 5 times 0.015. So let's see what that gives. Okay, what did I do here? Let me see. Okay, so according to my calculations, this works out to be equal to 5.2 times 10 to the minus 4. And then, of course, we need to find the percent dissociation, which is what the question is asking for. And that would be equal to 5.2 times 10 to the minus 4 m divided by the initial concentration, which is 0.015 m times 100%. And according to my calculation of that, that would turn out to be equal to 3.5%. All right. Okay, any questions about this? Any questions?
No.
All right. And is it okay for me to clear this here?
Yes.
Okay, let's scroll down. Or you know what, let's take a break right now since I lost some time the first 50 minutes of this class. I'm going to take a break here. It's now 30 minutes to 12, so we'll get back here at 12 o'clock, all right? Okay, I'm back again. All right, so we ended a while ago at number 10A. So now we're going to look at the B part. And basically they're asking again to calculate the percent ionization in the case of the B part. Okay, so let me see if you understood what we did in the A part, because that is important in order for us to do the B part. So let me hear your thoughts. What's the first step?
We know it's a weak base because they gave us KB. So we
Okay.
write out the equation to make the ice tables.
Okay, so NH4 OH to form NH4 plus OH minus. And as you correctly said, we set up the ice table. So initially, excuse me, you're going to have point.
What about the NH3 in parentheses?
Oh, okay. Very good question. So you can use this representation as well as this representation to represent the same thing, which is ammonia dissolved in water. Now, I decided to use this here to show the dissociation. However, you could just as well do this. NH3 plus H2O to form NH4 plus OH minus. So both equations are basically different ways of representing the same thing. They both have the same products in the end, but the reactants are different. So it doesn't matter which one you use, to be perfectly honest. I could have used this for the ice table, but I've decided to use this. All right. Okay, so 0.20 here would be the initial concentration of the ammonium hydroxide. And here you're going to have 0 and 0 here. And therefore, the change here would be minus X like we did before, plus X plus X. So at equilibrium, you're going to have 0.20 minus X. Here we're going to have X and X. And in this case here, what we're going to write down is a KB expression. And that would be equal to the concentration of NH4 plus times the concentration of OH minus divided by the concentration of NH4 OH. And then we plug in the different terms. You're going to have X squared over here divided by 0.20 minus X. And then now we're going to assume that X is much less than 0.20. So that means that 0.20 minus X is approximately 0.20. So this equation would simplify to X squared over 0.20 minus, 0.20. And that would be equal to the KB, which is 1.8 times 10 to the minus 5. So that implies that X is equal to the square root of 0.20 times 1.8 times 10 to the minus 5. So let's see here. 0.2 times 1.8 times 10 to the minus 5 equal, and then find the square root. And according to my calculations, this works out to be equal to 1.9 times 10 to the minus 3. And again, we have to find the percent dissociation, which is what the question is asking for. And that is equal to, in this case, the concentration of OH minus over the concentration of the original concentration of the of the ammonium hydroxide times 100%. So that would be equal to 1.9 times 10 to the minus 3 m divided by 0.20 m times 100%. And let's see what that gives. So 1.9 times 10 to the minus 3 divided by 0.2 times 100. Okay, so what I got is 0.95% as the answer. So this is the final answer right here. All right. Okay, any questions about this particular problem? Any questions? Okay, can I clear this?
Yes.
All right. Let's see what's next. Okay, so in this case, they're asking for the pH of these solutions, all right? And the first one is a 0.20 M solution of hypochlorous acid, and it gives you the Ka. Oh, before I forgot to mention something. I've provided in Canvas a table that contains the Ka values of pretty much most of the weak acids and weak bases for Kb values that you're going to need. So this table will be made available to you during your next test after this first test right here. Let me see if I can find it here. So if you go to tables, you're going to see here it says dissociation constants. In fact, these two are the same. It doesn't matter which one you click on. I'm going to get rid of one of them. But anyway, let me download this. Okay, so this is a table that you'll have access to not only now, but like during your tests. And the first part gives you the Ka, let me make this bigger, gives you the Ka values for different acids. And you'll notice that there are some cases there are more than one Ka values, right? And that's because there are some acids that can release more than one hydrogen ion, such as in the case of arsenic acid right here. As you can see, there are 3 hydrogens here. So if you lose the first one, the Ka value for that is 5.8 times 10 to the minus 3. For the second one, it's 1.1 times 10 to the minus 7. And for the third one, is 3.2 times 10 to the minus 12. All right, so that's basically what that tells you. And then below that, you have a list of Kb values. It's a shorter list of weak bases. All right, so those are the Kb values for the weak bases. And above you have the Ka value for the weak acids. All right. Okay, so I just thought I should point that out to you because during your next tests, you will be provided this table so you can use it to solve problems like the one we have been doing. So let me go back to.
I have a question about the test we're about to take or should be taking this week, either way.
Yes, ma'am.
Are they going to automatically know what to give us and what are we allowed to bring with us?
Yes, because whenever I submit tests in the testing center, there's a form that I submit with it. And on that form, I basically give information about what is allowed and what is not allowed. So they should provide, based on information that I would have provided in that form, they should provide, for example, the periodic tables and whatever else you need as far as that is concerned. In fact, the only thing you need to provide are your pen for writing and your calculators. But even
you want us taking the test in pen as well?
Yes. And even scratch paper, I told them that they should provide for you as well.
Okay, thank you.
Yeah. All right. Okay. Okay, so going back to the assignment, question number 11A, you're asked to find the pH of the solution. So what would be your first step?
Write the equation.
Okay, so the equation in this case, I'm just going to use HA again. Don't need to write out the entire formula for the acid. So that's going to be H plus A minus. So initial, you're going to have 0.20. You're going to have 0, 0. The change here will be plus X, I'm sorry. Plus X And here you're gonna have 0.20 minus x, x and x. So Ka will be equal to x squared over 0.20 minus x. Assume x is much less than 0.20. That means that 0.20 minus x is approximately equal to 0.20. So that simplifies this equation to x squared over 0.20 equals to Ka, which is 3.2 times 10 to the minus 8. So that means that x is equal to the square root of 0.20 times 3.2 times 10 to the minus 8. So that's going to be 0.2 times 3.2 times 10 to the minus 8. So that would be 8.0 times 10 to the minus 5. Make sure I'm doing the right thing. Let me do this again. 0.2 times 3.2 times 10 to the minus 5. And then find the square root of that. Okay, so I did something wrong here.
You did it wrong the second time. You said 10 to the minus 5. It should be 10 to the minus 8.
Yeah, you're right. So let me erase this here. So let me do this again. So it's 0.2 times 3.2 times 10 to the minus 8. And then find the square root of that. And that is 8.0 times 10 to the minus 5. And then we do the percent dissociation to see if our assumption is valid. So that's 8.0 times 10 to the minus 5. I think it's valid. Divided by 0.20 times 100%. And according to my calculation, this works out to be equal to 0.040%. So this is definitely less than 5%. So therefore, we can say that the concentration of X is equal to the concentration of H plus, which is equal to 8.0 times 10 to the minus 5 M, which means that the pH is equal to minus log of 8.0 times 10 to the minus 5. So let me do that. And according to my calculations, this works out to be equal to 4.10. And that would be the pH that the question is asking for. All right. Okay, any questions about this example or this question? All right. Is it okay for me to clear this? Going once? Going twice?
Yes.
Okay. Scrolling down. Let's see here. Okay, now this one, now there's something I need to talk about before we move on to this one. So let me go to my writing application here. No, not that. That's PowerPoint. So let me clear this here. Okay, now we talked about acids and conjugate bases and bases and conjugate acids, right? So I'm going to start off with a hypothetical example. So HA can dissociate, right? We're assuming that this is a weak acid, right? So HA can dissociate to form H plus and A minus, all right? So remember now, this is your acid. And this is your conjugate acid. I'm just going to put Ca here, right? Now, the thing about the conjugate acid, I'm sorry, this is a conjugate base, not acid. Let me erase this here. Because the conjugate base is what is formed when an acid loses a hydrogen ion, all right? So the thing about the conjugate base is that it can act as a base by taking a hydrogen ion from a water molecule to form back the weak acid and the hydroxide ion, right? So by virtue of the fact that the hydroxide ion is formed, that means that the A- is acting as a base when it reacts with the water. Okay, now what I'm going to do here is write down the Ka expression for the weak acid, which is the concentration of H plus times the concentration of A minus, all divided by the concentration of HA, all right? For the Kb expression for the weak acid, for the conjugate base, that would be equal to the concentration of HA times the concentration of OH minus, all divided by the concentration of A minus, all right? Now, if I were to add these two equations together, right, that will cancel out, and this here will cancel out, right? So you'll be left with, oh, and by the way, this will cancel out as well, and this will cancel out as well, right? So you'll be left with what? H2O to form H plus and OH minus. And you should recognize this as what? What do we call this reaction? Anybody?
Is that equilibrium?
Well, it's equilibrium, but there's a specific term to describe the dissociation of water in this way. We call this what?
Neutral?
Ionization of water.
Well, more specifically, the auto ionization of water, all right? And we know that the equilibrium constant, when we add two equations like this, right? The equilibrium constant for the net equation, how do we get that? Using these equations,
Ka
right?
times Kb.
I'm sorry?
Ka times Kb.
Exactly, Ka times Kb. So look what happens when we multiply this expression here by this expression, right? I'm going to do that down here. So you're going to have K is equal to the concentration of H plus times the concentration of A minus divided by concentration of HA multiplied by concentration of HA times the concentration of OH minus divided by concentration of A minus. So what happens as a result is that the concentration of HA will cancel out, the concentration of A minus will cancel out, and we're left with concentration of H plus times the concentration of OH minus. Again, this is something it should look familiar to you, so you should be able to tell me what that equals to. Concentration of H plus times concentration of OH minus is equal to what?
Is that 1.0 times 10 to the negative 14th?
Exactly, 1.0 times 10 to the minus 14, which is the ionic product of water, Kw, all right? So basically what this is telling us, right, is that the product of the Ka value for weak acid multiplied by the Kb value for the conjugate base is going to be equal to 10 to the minus 14. So can I erase all of this here?
Yes.
All right, so let me get rid of this here. So basically, to summarize, what we have just figured out is that the Ka for weak acid multiplied by the Kb for the conjugate base of that acid is going to be equal to 1.0 times 10 to the minus 14, all right? So there are two things that will be equal to the Kw, which is 1.0 times 10 to the minus 14. Ka times Kb and the concentration of H3O plus times the concentration of OH minus, right? That would also be equal to Kw, which is 1.0 times 10 to the minus 14, all right? So this relationship will become important in the question that we're about to do, but it's very important that you understand the relationship between Ka and Kb. Ka for weak acid and Kb for the conjugate base of the acid. Now, before we get to that question, I want to say one thing about this relationship. What this relationship tells us is that there's an inverse relationship between Ka and Kb, right? In other words, the stronger the acid is, or the larger the Ka value is for the weak acid, the smaller would be the value for the conjugate base for Kb, all right? So there's an inverse relationship. So therefore, if Ka is very high, which means that the acid is very strong, then the conjugate base Kb will be very weak. So just to give you a couple of examples, hydrochloric acid is a strong acid, very strong. So strong that all the HCl molecules will dissociate to form H plus and Cl minus. So the conjugate base of the hydrochloric acid is the chloride ion. This is very weak, very weak. So what that means is that, and this is very strong. So what that means is that the chloride ion, right, will basically not react with water to form the hydroxide ion and HCl. This reaction will not take place because the chloride ion is a very weak conjugate base, all right? On the other hand, let me do some erasure here. Let me erase this top part here. On the other hand, if you take let me see here. I'm trying to think of a good example of a strong base. Oh, okay. If you take, let's say, I'm trying to think of a good example. If you take, let's say, let me see. Okay, this one is a bit unusual, and that's because I can't think of a better example. But this one is from organic chemistry. This here is a very strong base, has a negative charge here, right? If you put this in water, it will immediately react by taking a hydrogen ion here from the water to form a gas known as methane, right? Plus OH minus, all right? So this is a strong base, very strong. And the resulting conjugate acid is this, which is very weak, all right? So that just basically shows you the inverse relationship between a base and an acid, or a base and a conjugate acid and vice versa, all right? Okay, so I just thought I should, explain all of that before we move on to the next question, because the next question says, oops, let me get out of this here. The next question says, you're to find the pH of this solution. Now, this solution here is sodium cyanide, right? Sodium cyanide contains the sodium and cyanide ions. Now, the first thing I would do, which is what we have been doing all along, is write down the equation for the dissociation of sodium cyanide. Now, you should remember from your general chemistry 1 that any sodium salt is very soluble in water. And that is true for basically the salts of any group 1 element, right? And sodium is from group 1. So basically what will happen first is that the sodium cyanide will undergo complete dissociation to form sodium and the cyanide ion. Now the cyanide ion is basically the conjugate base of hydrogen cyanide, which is the reason why they gave you the Ka value for it right here, right? So basically, because you know that the hydrogen cyanide is a weak acid, you have to look at what happens when the cyanide ion react with water. All right. So basically, an equilibrium will set up where you're going to end up with HCN plus OH minus, right? Because the cyanide ion is a conjugate base of a weak acid, right? So the cyanide ion will gain a hydrogen from the water to form HCN, and the other product or the byproduct of that reaction would be the hydroxide ion. Now, because sodium cyanide undergoes complete dissociation, whatever the molarity of this is, the molarity of this will be the same. So we can place that value of 0.055 here as the initial concentration of the cyanide. We're going to have 0 for this and 0 for this. And we don't need to concern ourselves with the water, right? Because the water, there's a whole lot of it there, and therefore its concentration will not change, especially because it's a liquid right there. We're going to do the same thing as we did before. We're going to look at the changes. So this will be minus X, this will be plus X, and this will be plus X, all right? And then we're going to write down the equilibrium terms. Here we're going to have 0.055 minus X. Here we're going to have X, and here we're going to have X. So what we're going to do now is write down the KB expression, because remember now, the cyanide is acting as a base. KB is going to be equal to basically X squared divided by 0.055 minus X, which again, we're going to assume in this case that X is less than 0.055, which means that 0.055 minus X is approximately 0.055, all right? Then we're going to put the result of that assumption, which would be KB is equal to X squared over 0.055. And then we're going to rearrange this to get X is equal to the square root of KB times 0.055. And that will be equal to the square root of, okay, so here's where things become interesting, because we do not have KB for the conjugate base, but we have Ka for the acid, which is 4.9 times 10 to the minus 10. Now remember we said that Kw is equal to the product of Ka for the weak acid multiplied by Kb for the conjugate base. So therefore, we can say that Kb is equal to Kw divided by Ka. And we can put that value right here. So here we're going to put Kw divided by Ka, Ka, multiplied by 0.055. So that would be the square root of 1.0 times 10 to the minus 14 divided by 4.9 times 10 to the minus 10 times 0.055. So that's what we're trying to find. We're trying to find the X, which is equal to all that there. And according to my calculations, this works out to be equal to 1.0 times 10 to the minus 3 m, right? And of course, we have to find the percent dissociation. In fact, let me erase this right here. So that's where I'm going to do the calculation of the percent dissociation. So let me say that, hold on, is this working? Okay, so percent dissociation is equal to 1.0 times 10 to the minus 3 m divided by 0.055 m times 100%. And let's see what that gives. So 1 times 10 to the minus 3 divided by 0.055 times 100%. So the calculation results in the percent dissociation being equal to 1.8%. So that means that's less than 5%, which means that the assumption is valid. So therefore, we can go ahead and use this as the concentration of OH minus because that's what the X here represents, the concentration of OH minus. So that means we can find the POH, whoops. The POH is equal to minus log of 1.0 times 10 to the minus 3, which works out to be equal to 3.00, which means that the pH, which is what the question is asking for, is equal to 14.00 minus 3.00, works out to be equal to, let me write it here, 11.00. And that's basically how that is done. All right. So this one is a bit more complicated because you're given a compound which acts as a base, but we don't know what the Kb value is directly because we do not have that information given to us. But we're given the Ka value, and based on this relationship right here, if you know the Ka value, you can easily calculate the Kb value because Ka times Kb is equal to Kw. So that's how we got this part right here. This here represents Kb, Kw divided by Ka, and all we have to do is the number crunching to get the concentration of OH minus, then the POH, which is 3.00, and then the pH, which is 11.00. All right. Okay, any questions about this particular example or problem? Any questions? Any questions? Okay, so now that we have done the B part, well, firstly, can I clear this? Going once, going twice. Okay, I'm going to clear this. And I'm going to scroll down. Now, I'm very interested in hearing what you have to say about the C part. How would you deal with the C part based on what we did in the A part? What's the first step you take?
Write the equation.
Mm-hmm. Okay, let me do that up here. So when ammonium chloride dissociates, it forms NH4Cl, well, NH4Cl, dissociates completely to form NH4 plus and Cl minus. All right, that's the first step. Okay, so what would be the next step?
To do another equation for the dissociation of NH4.
Okay, so what would that equation be? NH4 plus? When
Would
that
be
go ahead.
to NH3
Mm-hmm. Plus NH3 plus what?
H plus.
Okay, very good. Now in this case here, this would be another equilibrium situation, right? So what would be the next step?
The ice table.
Okay. So here you're gonna have 0.35. Here you're gonna have 0 and 0. Initially, I'm sorry, change will be minus X here, plus X here, plus X here. And at equilibrium, you're gonna have 0.35 minus X. Here you're gonna have X, here you're gonna have X. Okay, very good. What's the next step?
The Ka equation.
Ka. And I'm impressed that you said Ka. Why did you say Ka and not Kb?
Because there's H plus as a
Hey.
product.
Exactly, it's acting as an acid. Very good. So Ka would be equal to what?
X squared over 0.35 minus.
0.35 minus X, right? And then we're going to assume that X is much less than 0.35. So that means that 0.35 minus X is approximately 0.35. Okay, what next?
You could like write out how you would solve for X, which would be KA times 0.35.
Okay, so
square
X is equal to square root of KA times 0.35. What next?
You do the relationship between KA, KW, and KB. So you would
Okay.
have KA equals KW over KB.
So KW divided by KB. Okay, very good. Times 0.35. So basically, let me just make sure that this is done correctly. So basically, that will be equal to the square root of KW, which is 1.0 times 10 to the minus 14, divided by KB, which is 1.8 times 10 to the minus 5, multiplied by 0.35. All right. Very good. So when I did that calculation myself, I got 3.0. No, I'm sorry, I'm looking at the wrong thing here. Wait a minute. I got 1.4 times 10 to the minus 5. 1.4 times 10 to the minus 5, right? What's the next step?
That would be the concentration of H plus. But
Okay,
then you have to do the percent I to confirm it.
percent dissociation, which is equal to 1.4 times 10 to the minus 5 m divided by 0.35. And again, I think this is going to be less than less than 5%. Let me do that now. So that's 1.4 times 10 to the minus 5 divided by 0.35 times 100. Oh, what did I do? 1.4 times 10 to the minus 5 divided by 0.35. Okay, so I got 4.0 times 10 to the minus 5. Okay. So I got 4. Hold on, wait a minute.
I think you forgot to multiply by 100. Because I got that before multiplying by 100.
Me too.
Okay, I'm sorry. I just lost track of my thought a while ago. So that would be,
It would end up being 4 times 10 to the negative 3.
yeah, you're right, times 100. So yeah, 4.0 times 10 to the minus 3%, which is definitely less than 5%. So the assumption is valid. So what does that mean? What's the next step?
We can plug the H plus value into the pH equation.
Exactly. So pH would be equal to minus log of 1.4 times 10 to the minus 5. And according to my calculation, this works out to be equal to 4.85. And that's how that is done. All right. Okay, any questions about this one? Any questions? Okay, can I clear this? Going once. Going twice. Okay, let me clear this. Let's scroll down. Okay, so I want to hear what you guys have to say about this one. They gave you 0.50 m ammonium hydroxide. They gave you the KB value for that.
You start with the equation.
Okay, so that equation would be what?
NH4OH goes to NH3 plus OH negative.
Well, actually, it would be NH4 plus
Oh,
OH negative, right? And in this case, it's a weak base, so let me erase this here and make it more decent. So, okay, what's the next step?
you do an NH4 plus equation?
I'm sorry?
Would you do an equation?
No, because this is just a weak base. You see, the other two examples that we looked at, they were salts. The sodium cyanide and the ammonium chloride, they are
Oh,
salts.
okay, then you just do the ice table.
Okay, very good. So initially would be 0.50. Here you're going to have 0 and 0. The change here would be minus x plus x plus x. And then at equilibrium, you're going to have 0.50 minus x. Here you're going to have x. Here you're going to have x. So what's the next step?
Making a KB equation.
Okay, so KB is equal to what?
X squared over
X squared over
0.5 minus X.
and again, we make the assumption that x is much less than 0.50, which means that 0.50 minus x is approximately 0.50. So that means that KB is equal to x squared over 0.50, which means that, let me go down here, x will be equal to the square root of KB times 0.50, which will be equal to the square root of 1.8 times 10 to the minus, whoops, times 10 to the minus 5 times 0.50. 1.8 times 10 to the minus 5 times 0.5. And then I find the square root of that. So according to my calculation here, according to my calculation here, this works out to be equal to 3.0 times 10 to the minus 3. Again, we do the percent dissociation thing. And that would be equal to 3.00. I'm sorry, 3.0 times 10 to the minus 3 m divided by 0.50 times 100%. And that works out to be equal to 6.0 times 10 to the minus 3. Oh, I forgot to multiply by 100. I keep forgetting to do that. So this gives you 0.6, which is less than 5%. So that means that the assumption is valid. So what's the next step?
You have the concentration of OH negative, so you plug it into the POH equation.
Okay, so POH is equal to minus log of 3.0 times 10 to the minus 3. And that, according to my calculations, is 2.52. So what's the next step? Let me do it up here.
To get pH, you would do 14 minus that value.
14.00 minus the 2.52. And according to my calculation, that works out to be equal to 11.48. Is that rain? Oh, yeah, it's raining outside. Yeah, 11.48. All right. Okay, any questions about this one? Any questions? Any questions?
No.
All right. And And is it okay for me to clear this?
Yes.
All right. Okay, let me see here. Let me scroll down. Okay, number 12. We should make short work of this one before our next break. It says, what is the pH of a solution that is 0.25 m of a 0.25 m weak acid that is 2.2% ionized? So, any ideas?
Would you work the ionization equation backwards?
Okay, let's see. Let's remind ourselves of the ionization equation. More specifically, the percent ionization or percent dissociation. Percent dissociation is equal to the concentration of H plus at equilibrium divided by the initial concentration of the acid. I'm going to use HX since I have HX here, times 100%. So what the question is asking for is this. So based on this equation, what would be the expression for the concentration of H plus at equilibrium?
Is it 0.25 because it's a 1-to-1 ratio?
Nope, it's a weak acid. So you can't
Oh.
make that assumption.
So we have to solve, like, do
You have
it.
you have to solve for this equation right here, but you have to solve for this. That's why I put this here. What is this equal to in terms of all the other terms here?
Oh, it would just be the percent dissociation times the initial.
Right, it's going to be the percent dissociation, actually divided by the 100%, of course, multiplied by the initial concentration of the weak acid. So when we put the numbers in, it's going to be, let me see here, it's going to be 2.2% divided by 100% multiplied by the initial concentration, which is 0.25 m. And according to my calculations, this works out to be equal to 5.5 times 10 to the minus 3 m. And therefore the pH is equal to minus log of 5.5 times 10 to the minus 3. Whoops. And according to my calculation, that would be equal to 2.26. And that's how that is done. All right. Okay, any questions about this one? Any questions? No questions? Okay, so I'm going to take the next break now. It's now what, 12:48. And I'm going to restart at 1 and then we'll just finish up. I'm going to explain something which is probably covered in the videos, which I think I need to make sure that you understand it. So I won't be doing any more problems, but I'm just going to explain one last thing about the pH of salts. All right, so I see you guys at 1 o'clock. Okay, I am back. So, as promised, what I'm going to do now is talk about a topic which should have been covered. In fact, I'm sure it's covered in one of the videos I've left for you to watch. But I think I'm going to talk about it here, just in case, you know, you may not be clear on what was discussed there. Let me clear this first. And in fact, let me get out of this here and go to this here. And let me clear that. All right, so what I'm about to talk about has to do with acid-base properties of salts. Properties of salts, because you may have learned in Chem 1 or high school chemistry, introductory chemistry, you may have learned about the neutralization reaction, the reaction between the acid and a base to form salt and water, right? And the whole idea behind this is the fact that the acid is acidic, the base is basic. When they combine together, they give you a salt, which should be neutral, right? That is not 100% true. It's true in some cases, I would agree, but not 100% true. And what we're going to look at is how do we predict whether or not a salt is acidic or basic. So let's say you have a salt I'm going to represent with Ma, right? And let's say that Ma dissolves completely in water to form M plus and A minus, all right? Now, in order to make a prediction as to whether or not the salt is acidic or basic, you have to ask yourself the question, how will each of these interact with water, right? If this interact with water to form H plus MOH, then this would contribute to the acidity or basicity of the solution. If A minus reacts with water, it's going to react to form HA and OH minus, which would make the solution more basic. So the question now becomes, which one is in greater amount at this juncture? If the OH minus is in greater amount compared to the H plus, then the OH minus would make the solution basic. On the other hand, if H plus is greater than the OH minus, then the resulting solution is going to be acidic. So let me just go through a couple of examples so that you see how this works. So let me get rid of this here. And I'm going to start off with this salt, sodium chloride, all right? Sodium chloride dissociates to form sodium ions and chloride ions, right? Now, if the sodium ions were to react with water, these would be the products. You're going to end up with NaOH and H plus, right? If the chloride ion were to react with water, then you're going to get HCl and OH minus. Problem is, well, not a problem, but the fact is that the sodium is not going to react with water very much because the sodium ion is very stable, and the same is true for the chloride ion, right? So therefore, these two would have no effect on the resulting pH of the aqueous solution. So therefore, you won't have any extra H plus being produced. You won't have any OH minus being produced. So therefore, the sodium chloride solution is neutral. All right? Because you won't have any H plus or OH minus produced as a result of the ions reacting with water. All right? So that's why any solution of sodium chloride will have a pH of 7. Now, let me give another example. Let's say you're given ammonium chloride instead of sodium chloride. In fact, let me get rid of this here again. Okay, so ammonium chloride. Now, in the case of ammonium chloride, when this dissociates, you're going to have the formation of ammonium ions and chloride ions, right? Now we have to ask ourselves, how will each of these react with water? We already know that the chloride ion will not react with water from what we talked about before. But in the case of the ammonium ion, this is what's going to happen with water. You're going to have NH3 plus H3O plus, all right? Now, because you have the formation of the hydronium ion, that means that this solution of ammonium chloride will be acidic. All right. So no interaction with water as far as the chloride ion is concerned, but the ammonium ion will interact with water to make the solution more acidic. All right. Okay. So ammonium chloride is acidic. Now, let me show you another example. In this case, we're going to look at sodium acetate, which is C2H3O2. When that reacts with water, you're going to have Na plus C2. I need to change my writing tablet. This is messing me up. Okay, so plus C2H3O2 minus. Again, based on what we discussed before, the sodium will not react with water, so there will be no hydronium ion produced. But in this case here, the acetate will react with water to form acetic acid, which is HC2H3O2 plus OH minus. So in this case, the resulting hydrolysis or reaction with water of the acetate will produce the hydroxide ion, and therefore that will make this solution basic. All right. Okay. One last example I want to show you. Any questions so far based on what I've just discussed? Any questions? Any questions? All right. One last example I want to show you is ammonium acetate. So ammonium acetate is NH4 plus. I'm sorry, NHC2H3O2. When that dissociates in water, you're going to get NH4 plus C2H3O2 minus, right? Okay, so in this particular case, what's going to happen is the ammonium is going to react with water to form NH3 plus hydronium ions. And the acetate is going to react with water to form HC2H3O2 plus OH minus. So in this case here, you're going to have the hydronium ion being produced as a result of the hydrolysis of the ammonium ion, and you're going to have the hydroxide ion produced as a result of the hydrolysis of the acetate ion. So the question is, what will be the result in terms of the pH of the solution? And the answer is, it depends. And what do I mean by that? Well, it depends on whether or not the Ka value for this dissociation is less than or greater than the Kb value for this dissociation. So if Ka is greater than Kb, then the solution will be acidic. But if it's the other way around, Kb is greater than Ka, then the resulting solution is basic. All right. So it all depends. And if I'm not mistaken, and I probably need to look up the values in this case, the Ka value is actually approximately equal to the Kb value for this case. In which case, if that's the case, then the solution would be neutral. All right. So that's basically how you can predict the pH of a salt solution. All right, whether or not the pH is greater than or equal to or less than 7. All right. Okay, I'm going to stop here for today. And I think what I'm going to do is continue to look at the rest of the questions. How many questions are left here? Let me see. There are, you have question 15, 16, 17. Okay, so 3 more questions left, right? So I'm going to work on those next class, which is on Monday, all right? Remember your test if you have not done so before. Now, make sure you do the test, of course, in a testing center. Everything should be provided, as I said before. Also, remember the deadline date for the assignment number 3. That is due tomorrow at midnight, all right? So make sure that is submitted by that time so I can have it to grade and get back to you over the weekend. Okay, no more time left, so I bid you farewell Enjoy your weekend, and I'll see you guys on Monday. All right? Take care.